Thanks for being here. This is Mahesh from USAM, and today's topic will be on assemblies of Inventor. So it's managing motion in assemblies of Inventor, and know the difference between constraints and joints. Most of the users of Inventor use constraints, but in some areas, in some scenarios, joints will come in handy for us and will do a lot more help than constraints. We'll quickly see the differences between constraints and joints, and also how to give motions using various options that are available in Inventor. So opening Inventor. So we have an assembly option here in the home page. Hope everyone knows. And we'll start from placing a model. Here we have an option to place models in a different ways. So the first one is place your designs which you have already done, and the second one is these two are the most probably used options, and the second one is place from content center. And the place imported CAD files will also can be done using the first option itself, place. If you're bringing some other CAD formats into assembly interface of Inventor, you can go and say place itself. It's not necessary for us to use the third option. And in case iLogic component is used and the electrical catalog browser is used, we can go for fourth and fifth option, but we are not going to see all those things here now. We'll strictly concentrate on joints and constraints. So before jumping into the joints and constraints, we should know the initial method of doing method of bringing the components inside an assembly interface. So we'll go and place a model. So this is just for representation purpose. So this is just to show the best practices to how to bring a part inside Inventor, that's all. So belt conveyor. So initially it is free to move, and we can zoom in and zoom out. It's not yet placed. Without placing, right click the mouse. We have an option called place grounded at origin and say OK. So what it does is Inventor automatically mates the origin of the part which we have brought inside the interface with the origin of the assembly. So that's actually place grounded at origin option, and this is necessary for us to do for the first object, because once it is grounded, it won't move further, and it will be more helpful for us to bring other objects and mate it together. So before starting with your assemblies, make sure that the first part which you bring has to be grounded. Okay, so I'll open a part which is already placed together, that is not assembled, but we have brought all the parts together. An Inventor allows you to bring all the parts in a click of a button or in a stretch. It's not necessary for us to bring each and every part one by one. We can select each and every parts which you have already done and bring it to the assembly in one shot. Okay, so here you can see this part which named as P1 base is grounded, and the pin symbol denotes that this is grounded and it cannot be moved, and the grounded part is our base part. So on top of it we are going to assemble everything. I'll go to view and say share it with edges, so that edges will be showing here. So the most important and most handy solution for us in constraint is the first one, mate. So this is where most of our constraint take place, and most of the scenarios will be answered by this single option called mate. So I've selected mate here, and by default in Inventor we have two different options. One is joint and another is in constraint. We'll see the differences of these two in upcoming minutes of this video. So we'll start with mate, and we'll quickly move on to the other options available in constraint as well as in joints. So once you have selected mate, this first selection will be highlighted automatically, and when you hover your mouse to any of the model or any of the faces, it will automatically select the face, and it will show arrow mark normal to position. So we'll join this part into here, and always the part which is going to be moved has to be selected first, not the grounded part. So we'll go here and select the base of this part and come back here and select this. Okay, say apply, and this won't be closed yet because we can still go and do other mates also. And I think this is not exactly in the mid plane. It's not. Yeah, this has gap. So we'll go to mid plane of it, and also which part this is, B block 2. Okay, so we'll select this mid plane and as well as this mid plane, but here we are not going to use the first option, we are going to use the second option, which is flush. What flush actually does is it actually aligns the two parts together. The first one will be made, it will stick the faces which we have selected together. But the second option, flush, will align the two faces which you have selected. So that's the difference actually. We'll select flush and select the mid plane, and it will actually align it together. It's not mated together. And to know the exact difference, so if I select this face and this face and say mate, this will come over here and stick it with this face. Whereas if I say flush, it will just align. That's actually a parallel mate, right? And here we have an offset option. You can go and say 1 inch, it will offset to 1 inch, and even negative values are allowed here, say minus. So from here to here there is an offset of minus 1 inches. Okay, so if I go for 0, there won't be any offset, say apply, but this cannot be moved also because we have aligned these together. To check for degrees of freedom, we have an option here in view, say degree of freedom, and it will show, it will represent the degrees of freedom here. And there is also a shortcut, Control Shift and E for elephant, and it will show the degrees of freedom. Control Shift and E for elephant, it will again switch off the degrees of freedom. Okay, so going back here, you can see this part doesn't have any motion or any degrees of freedom. We'll quickly go and delete it. So all the relationships, all the mates which we have already given will be recorded here in the folder called relationships. Drop down it and you can go and check where the mates we have given and to which phases we have given. It will highlight and show it here, and you can once you select it, will give an option to say offset, or you can even go and edit it. Again this will open, you can go and select these two, change selections which you have already made, or you can switch over between flush and mate. So all these options are available. We'll go and delete this part, and once I delete, go back to degrees of freedom, it shows a translation motion. So it denotes that this is free to move here. Okay, so we have a motion here, it is capable of moving, but we have to arrest this by this end, arrest this by this end, and it should move only to this end, and it has to be constrained, right? Without constraining, we cannot arrest it between these two areas. So for that also, we are going to use the same constraint which we already gave a flush between these two areas, but we are not going to give any offset. We are going to set limits. So drop down this, we have an option to say for limits, and maximum will be, I think this will be around 4.5 or 5. We'll check with 4.5. I too don't know the exact length of it. And minimum will be 0 because this is the minimum value. The initial stage is 0. Say apply. Okay. So now when you move it, it will move till 4.5 and it will stop there. It won't move beyond it. And coming back here, it won't move beyond 0. So here we have options to constrain along with giving some limits so that it won't move beyond the given limit. And wherever you give limit, we have an option to drive it, that is to animate it. Go and say drive, we'll have a browser like this, a dialog box like this. Say play, so it'll automatically play the video. And we also have two options to check for collisions. If there is another option, we'll do that now. And this is the total number of steps which is going to do the increments of animation. And the repetition is, it won't stop. So after playing, it stops, right? Start to end. If I give start to end and say play, it will be keep on playing. So for 5 times it will keep on playing. And to reduce that speed, you can go here and say 10. UL is unitless. So wherever you see UL in Inventor, it's unitless. Okay. So the speed has been reduced. You can see the difference. So we'll check what this collision actually does. As of now, we'll close this. We'll quickly make this also, just to check for collision during our driving option. Okay. So we'll come back again, say drive, check for collision detection, play. And it has detected the collision in 0.45 inches itself. So that's the option for it. So we'll quickly close this and move on to the next option here. So here we have a cylindrical part which has to mate it here, and everyone knows, most probably those who are using Inventor, we can use mate option itself to do this, right? So go to mate, select this axis and this axis, it's mated together. And to change the orientation, you can click for the next option, it will automatically change the orientation. Say apply, but now it's still free to move. So we'll go here, sorry. So we'll select this space and this space and say align. It's aligned together, apply. So when we are mating two parts which both are not grounded, it's difficult for us to check for motions in the part which we have mated. So for that purpose also, we can go and say grounded and check this is working properly. And once after selecting or checking it, or once after mating it, you can go and say ungrounded. Okay. And we have inserted this pin using mate option, and since we have done it using that, we don't have an option to lock this rotation, right? But in case if you want to lock this rotation, you can use another option which is available inside constraint called insert. So go to constraint, we have an option called insert. So this will automatically select the face and axis together. So I want this face to be mated to a part and the axis. So I'll select these two and come back here. So this face has to be mated here with the axis of the cylinder here. So say select this area and change the orientation, and it's done, right? Say apply. Okay. So now it's automatically done both. It has mated axis to axis as well as face to face. So in a single click we have constrained these two areas, right? But still we have rotation here, right? So I'll say grounded, so we can check for rotation. I have what I have did, then I have did grounded for this part. So I'll say grounded, and yeah, we still have rotation. Go back to insert, say edit, we have an option to lock the rotation here. Say lock rotation, say OK. So now the location has been locked. So hope I have given a clear-cut picture of what is assemblies mate does with comparison with flush and mate, along with giving limits and driving the motions of the limits. So now we'll come back here for motion. What motion actually does? It has two different options. One is for rotation and rotation. So this will work for gears, bearings, everything. So when a cylindrical body rotates, the another body which is in contact with the first body will also rotate. So that's the option here, and we have both options, reverse and forward, and we have options to give gear ratios. And the next one is translation. So it will be rack and pinion conditions, where a cylindrical motion will transform into a translation motion. So I'll quickly go and open a model. Here there is a cylindrical rotation and also a translation motion which has to be connected to each other. So when this is rotated, it has to move front and back. To achieve it, we'll go to constraint. We have translation motion here, that is rotation and translation. So before that, we'll select the parts which we are going to mate it together. I want hand assembly and the driving net which is available inside this area. I'll select these two and say isolate. Yeah. So when this is rotated, this has to move. That's our criteria. Go to constraint, say motion. So I'll select the next version of it, the second option. It requires the axis of rotation and the face for moving the translation, achieving the translation motion. We'll quickly select this axis and say this face, and Inventor will automatically detects the distance between these two. We'll go and say 0.10. For one rotation, it will move zero point 0.1 inches. So the units which have been set is inches. So for one rotation, it will go for 0.1 inches. And this is for forward and reverse. Say apply. Okay. So for each and every rotation, it will go to 0.1. It will move up to 0.1 inches. So we'll quickly undo the isolation and check whether the whole assembly works accordingly. So since the net and this part is connected to each other, it has been mated to each other. Once it is rotating, the components which are mated to the driving net is also being moved. And here you can see this is going beyond the contact area. So this has to stop here, but it's going beyond it. So you can see, so I'll select this, it has to stop here actually. So for these reasons, it's not necessary for us to go and check for collision. It's already visible. And setting limits also is not a good idea here. What we have here is we have an option called contact set. So whenever a part is coming into contact with another part, it will automatically stop its motion. So that's an option which is available in Inventor. So before that, we'll select which are the parts that will come into contact. So we already know that these areas are going to be in contact when a motion is implied in it. So we'll go and select these parts and say contact set, and this net say contact set, and also this area say contact set. And this is not enough, we have to activate the contact set. So for that, we'll go to inspect, activate contact solver, and now rotate your part. So once it touches the part, it will automatically stops its motion. So it's come into contact and it's not moving beyond it. So you can see Inventor doesn't allow it to move further, and I cannot even rotate further. And again going back beyond it, so we'll come to a closer picture. I'm not able to rotate once again. Yeah, I'm not, oh yes. So Inventor doesn't allow to move beyond it actually. So you can go and switch off the activate contact solver, and you can do your design part. And whenever you want to check for it, you can go and activate. So before activating, make sure that you have make your parts into contact solver, that is contact set. You have made your parts into contact set so that once it is activated, these all will be activated accordingly. So next, we have an option called translation. It is actually a tangent mate. Even we have here also a tangent mate. I didn't cover because it's as the name implies, whenever a straight area comes in contact with a circular area, the tangent mates can be used there. And if it's for motion like cam, we have a translation option here also. So I'll quickly open a model. Cam wall, open, say open. Yeah. So when this is rotated, it has to move up and down, and this applies the translation motion. Go to constraint, say translation. It has only one option. Like in motion, there are two. Here, this is only one option available. Select the translated part and go for the tangent area. It's applied. Say OK. So when this is rotated, this is also move accordingly. So this will follow the path actually. It will be keep on in contact with the tangent area. So this is actually implying motion to the tangent faces. So that's translation available in the constraints of Inventor. Now we have seen what are the different options available in constraints and how motions can be implied using constraint option in Inventor. The next part of this session is talking about joints or knowing about joints. Joint is nothing but a predefined constraints. This has a defined constraint where we are not going to do anything. Where, for example, in constraint we have mate as well as insert. What insert does? It automates the process of mating actually. I have to insert a bolt. What I'll do is we'll select axis to axis and then we'll go for face to face. But what insert that does, it automatically select the axis along with the face. It's actually cutting our two steps into a single step. What join does is it gives us prefabricated constraints. So we'll go and select if I'm going for a rigid where the degree of freedom is 0. It's not necessary for me to go and arrest each and every face, each and every plane together and say, okay, I have arrested each and every motion of a part. It's not necessary. We can go for joint and say rigid. It will automatically arrest all other degree of freedoms which you see there. And if it's a rotational, you select the two parts and say rotational. If you are going for a cylindrical mate, you can go and select these any two parts and say cylindrical. It will automatically imply all the constraints that are necessary for us to make these two parts cylindrical. So that's the added advantage of using joints. And I'll quickly open some of the models to explain how joints work. And before that, we also have an option to animate degrees of freedom. In productivity, if you drop down, we have an option called degree of freedom analysis. There you can go and animate your degree of freedoms. So you can see in a particular model where are the degrees of freedoms are applied, and still we have a degree of freedom in rotation for a cam. So if you select animate freedom and go back here and select here, so it will show in animation. So we'll go for some other areas, some other model. So I'll quickly come here and do my degree of freedom analysis. So go for animate freedom. Here we have 3 translation and 3 rotation, and you can see the animation there, right? So it's showing all the degree of freedom available. So this will give you an animated view of available degree of freedoms. So this most customer doesn't know this option. So I think this may help you in any other scenario of your assembling process. Okay, joints. I'll quickly open a model. Name the model. So going to assemble joints. So the main advantage of using joint is once you have used joint, the first one is it is prefabricated constraints. So it's not necessary to constrain each and every face for us. It's already constrained together, and they have named it as rigid, translational, rotational, everything. And if you are going for dynamic simulation and you have already used joints, it will automatically go and um, identifies all the joints together. Or otherwise, we have to specify the joints and the way how it's going to act in an assembly. We have to specify from scratch when you are going for dynamic simulation. If we have already used joints, it will take from there. It's not necessary for us to again give the constraints here when going to simulation. So going back here, joints. By default, Inventor has automatic. Yes, it will take some things automatically, but we'll go step by step. Rigid. So rigid is something where it doesn't have any degrees of freedom. And here we have numerous options to select. So whereas when constrain, we'll be having only face-to-face options. Here we have each and every points and direction also. Here we can see we can change the direction. So perpendicular direction is also possible. So I'll go and select the midpoint of it, and you can see um, this part, that is arbor frame is grounded. So always select ungrounded part first. So we'll go for this, and I'll go for this area, and the Inventor will automatically animate. So now it's constrained together, that is joined together, but still we have to align this, right? So we'll go for align, select this face and this face, so it's aligned. And for second option, we'll go and yes. So we have aligned, and this doesn't have any degrees of freedom. Say apply. Okay. So that is actually rigid. We'll go for another rigid here. So I'll select the inner face and here the face to face, and it's rigid. Apply, and the inner face and this face. So it's rigid. So we'll go for the second option, rotational. Rotational is something where an axis and axis will be mated or joined together, and still we have a rotational freedom, and there is no translation, only rotation is there. Okay. So for rotation, I'll select this origin and this origin. So origin to origin mate will be given, and we don't see any translation, we have only rotation. And same, we have align option, even offset is there. So gap defines the offset between these two area. Say apply, and I also have to provide rotational here. So I'll select this face and I'll go here and select the inner face. So this area and this area will get mated together, and you can see the animation of Inventor which shows that this is rotational, and you can go and see animation anytime after you're given your joints together. So we'll close this and check for the constraints. So this is not moving, this is rigid, and this is rotating, right? And even this part is also rotating. So all joints are working perfectly. I want this face, but not in a perpendicular direction. I want in a straight way. Yeah. No, 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 no. Yes. So the direction seems to be perfect. We'll come here and select this face. Yeah. No. Again, I have selected wrongly. Yes. So these two directions should match each other, and since it's rigid, it's not moving, we go for a slider, and yes, this is what we have to achieve. This motion is what we needed. Say apply. So now it's movable. Okay. The next joint will be cylindrical. So cylindrical is something where it has rotation as well as translation. So go for cylindrical. This center point, and here we have a center point. Select these two areas, and as of now Inventor shows motions without these two handle cap, but once you say OK or apply, the caps will automatically go over there, so that's not an issue. Close. I will check for motion. So this is moving up and down as well as rotation is there. Okay. And for locking this translation motion, we have options here. So go to relationships and select slide cylindrical and lock the motion of it. So here now it won't move up and down, only rotation is there. And also for aligning these kind of areas, some will face errors. So we'll check for, so if this is protected, many of the customers ask my relationship is failing. So if this is protected and we go to constrain and we'll select axis to axis, say apply. So we won't get any errors. So the next will be planar, I guess. Before applying planar, I'll delete the rigid which we already gave. Okay, so now this is free to move. Planar is something where this face to face will be mated together, but still it is free to move and free to rotate. So that is planar. And move over here, go to join, planar, select these two faces, and you can see the motion. So these two are mated together, but still it has motion, right? So that's planar. If you go for automatic, that's planar. And finally, we have an option called ball. This is similar to our rear view mirror in two-wheelers, and as well as analog joysticks. So that's same. So for going there, we'll go here and check whether the automatic helps here. It should automatically detect this is a ball joint. So we'll go for automatic and select these two, and yes, so it's automatically detecting this. This is ball relationship, and that's the power of automatic option in Inventor, where it will automatically detect which type of relationship you're actually trying to give. And this is the ball, so ball joint. So it'll be free to move, right? So by this I have finished showing the difference between constraint and joint, and the various options to give motions also. And that's for today. Thank you. You can give your feedbacks and comments in the chat box and even comment section of this video. We'll meet in next session with some other new topic. I still have a pending video of to do, that is iLogic part 2. We'll also have that in the coming sessions or the coming week. Thanks for being here. Thanks for your support.